This week, we're going to look at differential equations with a new twist. We're going to look at differential equations which have non-constant coefficients. And as a second topic, we're going to look at resonance with Laplace transforms in a couple of different ways. Looking at equations with non-constant coefficients, we focus our attention on this coefficient for the y prime here, and we note that the techniques we have from the course, none of them will work here. If you think of the y corresponding, which is something we might try to use here, for that we assumed that y was equal to e to the rt, but that was based on the fact that y prime, y double prime, and so on would end up canceling out. Now in this case here, if we put an exponential in for y prime, it's going to be a t exponential, and we're going to have two other separate exponentials. There's no way that's ever going to equal 1. So this method here is just not going to work at all. The second choice would be Laplace transforms, and that would be fine, except we're asking here for the Laplace of t times y prime. And so far at least, we can't do that. However, there certainly seems like more flexibility in the Laplace method than in this basic assumption. If we violate this assumption, it's very fragile. We don't have anything else to fall back on. However, we've seen transforms of other products before, so maybe if we do some work, we might turn that into a nice big check mark. So let's explore that some more. To be able to handle this product of a power of t and some second function, what we're going to need is a rule like this. The simplest version of this is in your table as well. When we take the transform of this product, we're going to end up with the transform of the original function by itself, the second function, and then it's going to be modified. So it's similar to the transformations that we saw earlier, like the Laplace transform of e to the at f of t. That gave us f of s minus a. So in this case, by having an exponential multiplier, we got the same transform, but with the s's replaced with s minus a's. Here we get the same transform of f of t again, but the effect of this multiplier is to actually cause a derivative to be needed, as well as possibly a negative sign. Now we're going to prove this, at least sketch the proof, for the n equals 1 case. So this is like Laplace transform of t times some other function. For example, Laplace of t e to the 2t, or Laplace of t sine t, things like that. What we're going to do is start from the other side and ask what happens when we take the derivative of the Laplace transform of some function. Well, the Laplace we have a definition for, so what we're going to do is integrate from 0 to infinity. We're going to put our function in there, and we're going to have e to the minus st dt. That's applying the definition. And once we've done that, what we're going to do next is take advantage of the fact that f of t has some nice properties, the continuity, piecewise continuity, and exponential order. All that together is going to let us swap the order here of the integration and the derivative. So that might seem pretty innocuous, but there's some ways to have that go wrong if you're not careful. For all our cases, this is going to be fine though. And so we end up with a derivative inside, and this we can actually evaluate. So if I wanted to differentiate this and be very, very careful, that's the derivative with respect to s. Then what do we get? Well, we get f of t is a constant with s. And the exponential's derivative is e to the minus st. The derivative of any exponential is the same exponential again, times the s derivative of this, which is negative t. Then we can tidy that up and write it as the integral from 0 to infinity of t f of t e to the negative st dt, just rearranging terms and putting a negative sign out front. And as soon as we do that, well, this is the Laplace transform of t times the original function f of t. And there's a negative sign out front. So what we just showed in reverse is that starting from this side, we end up with a Laplace transform of t times f of t with a negative sign out front. Once we've shown this for the first derivative with 1 power of t, then we can simply repeat or use induction for t squared, t cubed, and so on. You can see the pattern is going to remain the same. Every time we differentiate this exponential with respect to s, a t will pop out, and we'll have an extra t, and we'll also have another minus sign. So minus 1 to the number of t's, and the number of derivatives to the number of t's. Having discovered the most general rule for powers of n times some function, and then taking the Laplace transform, we can apply this to the simple case of t to the power 1, which will be the negative of the derivative of the Laplace transform of f of t. I'll simply write it like that because we know that this will have s's in it. And so it'll make sense to do the derivative after we complete the Laplace transform. With that rule in mind, we can now practice with the transform of some functions that we already know and have seen before. Recall that this function appears in the spring mass system when we have resonance. This is the function that starts off with low amplitude, which is this t value here. But because that t is multiplying the sign, what we end up with in the graph of this function is a sine function, but the amplitude is growing linearly with time. So we see that linear growth in the boundaries for this function. All that is aside when we go to take the actual transform of it. So here we're simply going to use this new rule. The Laplace transform of t sine of kt is going to be equal to negative 1 times the derivative with respect to s of the Laplace transform of sine of kt. So lots of brackets here. So the first thing we do is work our way out from the inside, and we take the Laplace transform of sine of kt. Leave the negative 1, leave this derivative. The Laplace transform of sine of kt is in the table. It's k over s squared plus k squared. Then we can apply the derivative to that. And that will give us, careful, the only s term is in the denominator here. So we would have k s squared plus k squared. This is to the negative 1. So we'd have the negative 2 times negative 1. And then we take the derivative of the inside from the chain rule. And we'd end up with, simplifying all of this, 2ks over s squared plus k squared all squared. And that would be the way we'd apply this rule for t multipliers to functions whose transform we already know.